Hello everyone. Today's lab is treatment of scientific data. We're going to see if we can learn some things about significant figures and making measurements. The idea of significant figures, sometimes called significant digits or sig figs for short, is that when you do a computation that you're not over-representing the amount of precision that you had, or that the result is not more precise than the things that you actually measured or the things you used to get that result. A good way to think about this is which digits are really giving me information about how precise my measurement is. We can consider these two rulers here. The question to ask yourself is which of these rulers is more exact? Ruler A, ruler B, and in regards to measuring the block in between. When considering ruler A, because of the subdivisions on the ruler, we can determine that the block can be measured to 4.7 units, maybe 4.8. Ruler B, because it has more subdivisions, can be measured to 4.82 units. It's more exact because it has more subdivisions, and you get more significant figures out of it. Notice that we're guessing what the last digit is too, and this is what you should do when making your measurements. This guessing is what we call interpolating. You also need to interpolate with different types of measuring devices, such as graduating cylinders. Graduated cylinders, this type of equipment has been designed and calibrated to carry a volume based on the liquid level reading at the bottom of the meniscus. So when you go to interpolate a graduated cylinder, you need to make sure that you get at eye level and measure from the bottom of the meniscus. For instance, the volume of this liquid should be recorded as 36.5 millimeters, or about, you may see 36.6 or 36.4. Because it measures to the ones place, we would record to the tenths place, or 0.1 milliliters. Remember to guess the last digit. That is interpolation. How many sig figs in a measurement? How many significant figures or significant digits are in a measurement? Remember, read from left and start counting significant figures when you encounter the first non-zero digit. All non-zero numbers are significant, so any numbers that are not a zero count as significant figures. The number 613 has 3 significant figures. The number 1, 2, 3, 4, 5, 6 has 6 significant figures. Zeros located between these non-zero digits are also significant, and they all count. 5004 has 4 significant figures, so those zeros in between are significant because they indicate the whole number. 602 has 3 significant figures, and this huge number, 6 with a bunch of zeros, the 2 at the end, has 16 significant figures. Trailing zeros, those at the end of a number, are only significant if the number contains a decimal point, because this implies further precision. Otherwise, they're insignificant. For instance, 5.640 has 4 significant figures. Because the 0 is trailing, all the numbers in this number count as significant figures. 120,000 has 6 significant figures because there is a decimal point behind the number. Some people like to follow the Atlantic-Pacific rule. The Pacific rule states that if a decimal is present, you need to start counting with the first non-zero digit from the left. So if you look at the left side of this slide, you can see that 0.0019 contains 2 significant figures. This is because the zeros are not in between non-zero digits, and they're also not trailing. 65.01 has 4 significant figures. This is because the 0 is not only between 2 significant figures, but it also, or 2 non-zero figures, but it's also behind a decimal point, and therefore, following the Pacific rule, this number has 4 significant figures. 0.0300, however, only has 3 significant figures, and that's because the 0 in front of the 3 is not between 2 significant figures, but also the 2 zeros trailing the 3 indicate more precision. This number has 3 significant figures. 700 decimal, because of the decimal, this number now has 3 significant figures. If you follow the Atlantic side, the Atlantic rule, on the right side of the slide, you can see with the decimal absent that we lose some precision. So 80,200 only has 3 significant figures. Those trailing zeros don't count because there's no decimal involved. And then we have 400,000. This number only has 1 significant figure, the 4. 32,105 has 5 significant figures. The 0 here counts because it's sandwiched between 2 non-zero digits. 700, 1 significant figure, the 7. So the Pacific rule states again that if a decimal is present, you can start counting with the first non-zero digit from the left, and this will help you tally up your significant digits. For the Atlantic rule, if the decimal is absent, you want to start counting with the first non-zero digit from the right. But then we also have this concept, this weird concept, called infinite significant figures. This applies to exact or counted numbers and conversion factors. For instance, 240 people would be considered to have infinite significant figures because of the designator of people. One oxygen atom in dihydrogen monoxide or water, H2O, is also considered to have infinite significant figures. And with conversion factors, 1,000 millimeters equals 1 meter, or 12 items equals 1 dozen. All of these are examples of things that have infinite significant figures. As a further on example, one of my favorite things to say is 40,000 water balloons. 40,000 water balloons has an infinite amount of significant figures, as well as the conversion factor of 1 gram is equal to 1 million micrograms. Because of these designators as conversion factors, the conversion factors themselves have infinite amount of significant figures and do not change the magnitude of your measurement. When it comes to significant figures, sometimes and often you'll need to add, subtract, multiply, and divide them. And there's different rules of thumb that you need to follow with this. When it comes to addition and subtraction, we're not necessarily concerned with the number of significant figures, but rather the number of decimals. Answers should have the same number of decimals as the measurement with the least number of decimals. You can only be as precise as your least precise component of your calculation. For instance, if you look at the calculation on the left, the addition calculation, you can see that the number with the least amount of digits behind the decimal is 225.2, which only has 1 number behind the decimal. This means that your answer can also reflect only 1 number behind the decimal. So when you add these 3 numbers together and get 1679.6179, this answer is far more precise than you can actually report. So you have to round your answer to only 1 number behind the decimal, or 1679.6. If you look at the example on the right, the subtraction, you can see that the least amount of numbers behind the decimal point are 0. So your answer cannot have any numbers behind the decimal point, or else it would be far too precise. Therefore, when you subtract 17 from 1203.12, your answer can only reflect the value of 1186. It can only be this precise and no more. A good way to think about these things are which digits are giving you the information about how precise your measurement actually is. When it comes to the multiplication rule of thumb, the calculated quantity can be no more precise than the data used in the calculation. So you need to report your answer to the measurement with the least amount of significant figures. If you look at the example on the left, multiplication, you can see that the component with the least amount of significant figures is 2.31. This number only has 3 significant figures. So when you multiply 362.56 times 2.31, your calculator may give you an answer like 837.5136. However, this is far more precise than you can actually calculate. And because the component of the equation that has the least amount of significant figures is only 3 significant figures, your answer has to be rounded to 3 significant figures as well. And your answer would be 338. If you look at the example on the right, it's division. You have 738.10 divided by 10.97. The component of this equation that has the least amount of significant figures is the 10.97. Because this number only has 4 significant figures, your answer can also only have 4 significant figures. And while your calculator may reflect the value of 67.2835, you have to round this value to 4 significant figures, or 67.28. Significant digits also need to be considered when using scientific notation. Scientific notation is a way to handle very small and very large numbers, and you'll use it frequently throughout your scientific career. When the last reported digit is a zero in a number and it needs to be significant, you can use scientific notation to reflect this. For instance, 230 contains two significant figures. But if you say 2.30 times 10 to the second, this contains three significant figures. So be careful when converting to scientific notation and be sure that you're reflecting the correct amount of significant figures. Another example of how to convert to scientific notation would be the number 10,200, which has three significant figures. To appropriately translate this to scientific notation, you need to reflect 10,200 as 10.2 times 10 to the third, which also has three significant figures. Then we can look at if there's a decimal involved, such as 10,200.0. Because of the decimal, this number now has six significant figures. And you need to reflect this in scientific notation as 10.2000 times 10 to the third. This also has six significant figures and would be the appropriate way to write 10,200.0 in scientific notation. Frequently with your measurements, you'll have to use conversion factors. When you're using conversion factors, you can change the units for a measurement. Conversion factors are always assumed to have infinite significant figures, and these are the conversion factors themselves, not the numbers measured involved. So when conversion factors are always equal to 1, they don't change the actual magnitude of the measurement and just the unit. Therefore, the precision stays the same. For example, 1 mile is 5,280 feet, but how many feet are in 3.5 miles? So you can look at 3.5 miles times 5,280 feet. The conversion factor itself doesn't change the precision of the measurement. And you end up with 18,000 feet. 18,000 feet has two significant figures, just like 3.5 miles has two significant figures. We can look at this a little bit more when converting things like 400 grams. 400 grams has one significant figure. There's 4,000 milligrams and 400 grams. So when converting, the answer 4,000 milligrams has the exact same amount of significant figures as the initial measurement, 400 grams, one significant figure. When looking at centimeters, 0.0060 centimeters only has two significant figures. If you want to convert this to millimeters, 0.0060 centimeters is equal to 6.0 millimeters, which also has two significant figures.